Hi, my name is Luca Antiga from TensorWork, and I'm here to talk to you about RedisAI that reached 1.0 in these days. We'll briefly see why RedisAI, then we'll get into how does it work, how does it integrate with lifecycle management tools like MLFlow, and we'll peek into how fast it is and see what's next for the next releases. So why RedisAI? We're seeing AI deployed in production more and more. One context is computer vision. Here you have to ensure low latency generally. You have image data streaming into your device. It's possibly you have to run more than one model at a time, and then you may or may not need pre and post processing on your image data. Usually requests may benefit from batching. Batching is processing more than one image in parallel, since the devices you run the computational are capable of massively parallel computations. Another very widespread application of AI these days is NLP, natural language processing. You have large billions of parameters models that can reproduce a conversation, generate text, understand text, translate text, act as a virtual assistant, keep state of the conversation, multi-turn, persistent in an interaction. Often you need reference data kept in memory, and sometimes it's not just running the model once, but running it multiple times using techniques like beam search, which unrolls a conversation in many possible ways and then chooses the one that fits best. So this means looping through requests as you serve your model. And then, of course, all the IoT and streaming data world analytics where you want to do, for example, anomaly detection, drift, predictive maintenance from devices generating a lot of data in time, or in financial institutions, fraud detection, transaction analysis. Here, typically you use much smaller models than what we have seen at the previous slide, but many times you use them in ensembles. So many of them together on data that flows in with a fast rate, and sometimes these systems are managed through Redis. So the data streams in already in key value stores in memory databases. And sometimes you also need reference data to compare against or to search in while you're running these models. So you need to keep it hot somehow. So all these applications hinge on a representation of data that is usually numerical and takes the form of a multidimensional array. Multidimensional array, also called tensor in deep learning lingo, drawing from mathematics. With this representation, you can represent scalars, 1D vectors, 2D matrices, 3D tensors, or really ND tensor. And a tensor is really a way to index a numerical representation of some quantity with multiple indices. And this numerical representation is passed through models that, through weights that they have, they incorporate, and they define their behavior, and through connections, produce other representations down to the output. And the output is, for example, in this case, a probability of having recognized something in an image. And this is also a tensor. And these models are, for example, in deep learning, are a sequence of instructions that involve, for example, matrix multiplications, application of nonlinear functions. For example, here we see sigmoid. And this graphical representation we see on the right is a serialization of a computation that is performed in a neural network. So for each step, you have a set of weights and biases, which are tensors themselves. You enter with x, which is an input vector. You matrix multiply that vector by the weights. You add the biases. You run them through a nonlinear function, and on and on until you get to the output. So really, a deep learning model is a program over tensors that can be serialized and described in two pieces. One is the sequence of operation. In a way, it's like having a virtual machine with a very specific instruction set running it, and binary blobs representing the weights and biases and the parameters of the model. So you can have all this in one binary blob that you can develop on your hand as a data scientist, and then deploy as a DevOps on a high performance runtime. Well, I think Iftak summarized very well what are the challenges in taking AI into production from the point of view of AI inference engines for applications that have to have high performance. You need fast end-to-end inference, so minimize the back and forth, minimize the downtime. So if you have to upgrade a model, the runtime should still work and without interruptions. You need to be able to scale from very small device to very, very large clusters. You should support multiple frameworks because you don't want your inference solution to be influenced too much on what is used for creating the models in your data science department. You want a solution that covers all scenarios. It must be easy to deploy new models, so the path from data scientist to production should be as streamlined as possible. And then you should have a way to understand what's going on in your model, what's being served, and so that you can monitor its performance, iterate quickly, and provide new versions as you iterate along your so-called active learning process that asymptotically takes your model in production to have the desired performance. And really, you need to be accustomed to a solution that you can deploy anywhere, be it an edge device again or a cloud infrastructure. The AI landscape has evolved and is evolving month by month. I would say that the challenge for 2020 is, and partly it was the same for 2019, is how we can take AI into production environments where production is can go from I build a model and I take it to production by putting it behind a REST API using a Python web framework, or try to push performance and use your hardware at scale as efficiently as possible. So a number of AI inference engines have been proposed lately. TensorFlow Serving, I think, was one of the first offered in the market, and I would say the last is arguably PyTorch Serve, which has been just announced a few weeks ago. And then NVIDIA is developing their own. It's called Triton Inference Server. And then we have a number of frameworks that have the possibility, they give you the possibility to deploy into production, like Catalyst Reaction for PyTorch, or also frameworks like Seldon or Kubeflow. Cloud provider are starting to offer their own serving solutions like SageMaker, Azure ML, and GCP AI. And there are other frameworks that allow you to do the same eventually as intermediaries between a cloud offering and the data scientist, to try to streamline this process as much as possible. So what is RedisAI? RedisAI is a high-performance AI serving solution that tries to address the needs that we set out and a couple of slides ago. So it tries to bring the operational effectiveness of Redis and AI serving together to bring a very nimble and effective solution to AI serving. Here we have a Redis instance on a machine that has CPU, GPU, multiple GPUs, and we suppose we load the RedisAI module in Redis. And at this time, we have the possibility to set a model, which is the serialized representation that I showed you a few slides ago. And the model can be represented or exported as a TensorFlow graph or a PyTorch program or Onyx protocol buffer. Onyx is an interchange format for machine learning and deep learning computations. And we support all three. So by doing that, you now have a model, and you can also set a tensor. Remember the multidimensional array representation. This becomes a data type in RedisAI. So we extended the Redis data types with these two key data types, which are the model, the computation, and the tensor, the data, the multidimensional array. And it's supported natively in RedisAI. And by using the model with a tensor in input, using the model run command, we can transform one tensor into another one, or more than one tensor into more than one tensors in output, so that we can get the output tensor. So this is the very basic way RedisAI works. And the computation can be carried out on the GPU or CPU, multiple GPUs, or even other types of devices supported by a specific backend. So in a nutshell, it's an enterprise-ready solution for production AI. It's been developed jointly by Redis Labs and TensorWorks, the company I represent here. It turns Redis into a high-performance serving engine. It supports multiple frameworks, so PyTorch, TensorFlow, or anything that can export the model to Onyx, which are nowadays many other frameworks, even in machine learning, not necessarily deep learning. It supports CPU, GPU, or other accelerators, whatever the backend supports, and we'll talk about backends in a second. And after 1 year, we announced RedisAI last year as a prototype Redis module, and now it's entering general availability. You can know more about RedisAI at the Redis website. We're developing everything in the open on GitHub, and here you see what the repo is. And recently, Redis Labs, and probably you know it from other talks, has launched a great discussion forum at this address, and we also have a RedisAI forum there. So you're encouraged to interact there with us, or open an issue on GitHub. And RedisAI is not something that is brand new and untested. At the parent company that TensorWorks spun off from, Orobix, which is a company I co-founded a number of years ago, we're using RedisAI in production in different environments, from very small devices like the NVIDIA Jetson TX2 that we use for industrial vision application, to servers with GPUs on top, which we use for either computer vision, industrial computer vision application, or medical imaging application, all the way to using it in a Kubernetes cluster on a private AWS cloud, which we're doing with a pharma company. So with RedisAI, we can really serve models throughout the spectrum of the applications we cover, and we hope the same can be true for other folks. What are the benefits of RedisAI? So you don't have to commit to an AI framework. You can run multiple models from multiple frameworks all together on the same machine if your memory allows. And you can also export machine learning models from scikit-learn, and thanks to OnyxML, execute them in RedisAI. You can leverage data locality because Redis is Redis, and you can store values at keys. So you can store tensors at particular keys. So you don't have to necessarily equip your serving engine in every request with all the data you need. You don't have to move data around so that the data reaches your model. The data is already close to your model, and you just make a request with a specific input at that iteration. And that has implications, for example, for conversational NLP agents that have to store the state of a conversation, for example, and you can keep it in Redis the same way you would keep a web session in Redis and serve multiple users through that same mechanism. We support A/B testing, since we can deploy without ever stopping Redis from serving requests, monitoring, and we'll see a bit more what the roadmap for that is. And of course, you can leverage all the features, operational features that RedisAI provides, like master replica, high availability configuration, or a cluster mode, all the way up to enterprise. We have a RedisAI enterprise configuration too that can leverage massive deployments. When should you use RedisAI? Well, when you don't want to pay extra for your serving. Serving models is typically done on machines that have a high cost, a high impact, because they have fast accelerators. And so you want to maximize the time you're actually using those accelerators as opposed to serving requests and so on. So this is really important for maximize the efficiency with which you serve models out there. When you don't know where you will deploy, or when you know that you will have to deploy from the edge to a spectrum of other scales, and you don't want to commit to a particular scale, you know that RedisAI will work well if you compile it for ARM and just use it on an embedded device up to large cloud clusters. You can also integrate it with other data structures that are present in Redis. So whatever data structure Redis provides, or whatever data structure other Redis modules provide, you can make them interact. And actually, if you followed will follow the Redis Gears talk, RedisAI is also integrated with Redis Gears. So you can involve a RedisAI inference step in a Redis Gear computation. And anywhere you need Redis for reliability and availability, that's where, if you think about Redis in a context of serving models, that is what RedisAI for. We have a set of clients. Actually, you can use RedisAI with any client, any Redis client, even the CLI, which is probably good for individual commands. But if you are from any programming language that you don't see listed here, you can really use the RedisAI from any supported client. But we also created RedisAI, specific RedisAI clients like RedisAI Pi, RedisAI Go, and JRedisAI for Java that will integrate a bit better with the ecosystem, and they will make it really painless to, for example, have in Python a NumPy array that you want to set at a key. And this is how you do it. You just initialize a client and you call TensorSet, which is the command for setting tensors at a key foo, and you provide it with a NumPy array, and all the conversion will happen behind the scenes. Same thing when you get a tensor. And similar things happen for Go and Java. To run RedisAI, well, building RedisAI is not very hard. You can clone, you build it using the providing make files that we created to streamline fetching dependencies and building. And then once you build it, or you download a pre-built RedisAI library, then you just have to invoke Redis server with load module and point it to the right shared library. We also provide Docker containers because it's a very effective way to get up and running with just one command. And so you can run Docker on a CPU instance, or for example, on a GPU machine. That's the command line you have to execute. And there will be Docker images for GPU, built for GPU. Thanks to Itamar Haber and Felipe from Redis Labs, we have a new documentation website that it's going to be very useful for those of you who approach the tool. We have quick starts, we have a conceptual introduction, and we'll be improving the documentation also based on the feedback you send on the forum. So please interact on the forum. If you see anything that needs better explanation, just let us know, or open a PR on GitHub. I'd like to delve a little bit on how RedisAI works behind the scenes, because it's a good way to get accustomed to what it does in detail. So we said that RedisAI introduces tensors as a native data type. What happens if you have a tensor on the client, which is usually represented by information of what numerical type, float, int 32, int 16, and so on, a shape. So for example, if it's a 2D image, for example, it could have a 28 by 28 pixels, or it could be any dimension, even a 4 or 5D tensor, and then binary data. And through the metadata above, you can go in the binary array to index numerical values there. So how do you set this into Redis? When you execute CLI command, for example, the second version of it, you have tensor set. You're setting the tensor at key foo. You specify the floating point representation on what you're sending on the other end. You specify the shape, which is rows and columns in the case of an image, for example. And then you can specify values. Values can be specified either by sending individual values, which gets inefficient very soon, or you can provide a binary blob where the binary representation of those values are stored. Of course, they have to match the numerical data type that you specify and the size. And when you do this, what happens is that RedisAI will store that tensor representation at a key. And this is how you do it in Python. We've already seen that a couple of slides ago. You create a NumPy array and you just set the NumPy array. And internally, that NumPy array will be queried for shape and numerical type. For models, the situation is actually simple on the RedisAI side, because once you have a serialized model, it's really easy to set it into a key and have that key correspond to that model, and assign it a device, for example, a GPU, so that it will be transferred on GPU and kept hot on the GPU for use. A bit trickier part is to get from a PyTorch code or TensorFlow deep learning model or other deep learning ML frameworks and export in the right format for execution into RedisAI. These are all formats that are not specific to RedisAI. They are specific to the framework you develop the model in. But in this case, every framework has its own way to generate the serialized representation of their computation. PyTorch has Torch script, and there's extensive documentation on the PyTorch website on how to convert to Torch script, a model to Torch script for execution in runtimes like RedisAI. In TensorFlow, we support GraphDef at the moment, so you will need to execute Python code that freezes your graph and exports it to a GraphDef protobuf. Again, there's documentation out there, but we also provide examples on how to do it, and we'll talk about that in a second. And then Onyx, many frameworks like PyTorch support Onyx out of the box, so you have two options for PyTorch. TensorFlow, there's a project that shows you how to export a TensorFlow model into Onyx and run it within RedisAI. When you set it, you have to specify the backend, whether it's Torch, TensorFlow, or Onyx runtime, and then a device where you want the execution to happen. So this is the way you do it from the CLI. You specify the key, the backend, the device. You can also specify GPU without column 0 if you just have one. And then you signal that the blob is following. And so you need to provide the binary blob, the serialized computation that you obtain from your framework of choice. And this is the way you do it in Python. So say you already saved a protocol buffer representation of the computation using, for example, framework. In this case, it's a PyTorch serialized computation. And then you can read it from the file and set it. When you set it, then you can execute it. Execution, of course, as you can imagine, is a long-running process. So instead of doing something in the main thread that would block RedisAI from serving requests, we run computation in worker threads. It's in a configurable number of worker threads per device. And per device because you don't want a computation on the GPU to wait for its counterpart on the CPU to finish. So we have separate worker threads and separate queues. So when you ask an execution for a model and that model has been set on GPU 1, it will end up in the queue for GPU 1, and then there will be a number of threads that consume the computation. By default, it's 1. Here you see a couple of other run commands that we'll talk about in the following slides. One is script run and one is DAG run. We'll see them in a second, but they go through the same mechanism. So first of the two is the script. It's similar to a model. It's a computation over tensors that can be executed on the CPU or on GPU. Scripts are provided as, instead of being serialized computations, they're directly provided as a torch script source code. So we already talked about torch script. Torch script is a subset of Python. It's actually its own language with a Python-like syntax that describes computation over tensors. It's provided within the PyTorch project. And in PyTorch, it's used to execute computations using the just-in-time compiler that PyTorch provides. It's a strongly typed language, so it's not dynamically typed as Python, but it looks like Python when you write it. It will throw its own errors if you don't do things right with types. So if a type for a variable changes, then it will throw an error upon execution. But this is something that can be managed quite easily if you look up what to do on the documentation. And we'll provide also examples on how to write scripts. Scripts are represented as their source code. When you set a script in RedisAI, it will be compiled as soon as it's set, and then it will be ready to run. And it will take inputs in the form of tensors and output in the form of tensors again. This is how you set a script. And this is how you set a script in Python. You have a function add2 that adds a and b, which are tensors. And so you return a plus b. And this computation can be set using script set at the key s to be executed on GPU 0. RedisAI scripts can be used, for example, for executing pre-processing steps that you don't want to actually trace or export, or if you have even a TensorFlow model and you need to do some pre-processing without actually creating a specific TensorFlow model for that step and exporting it, you can simply manage it with a torch script. So torch scripts can be used both with PyTorch models, but also with models from other backends. Same thing for post-processing. In this case, you have an input tensor that gets pre-processed, I don't know, for normalization, for example, directly maybe in the GPU, and then two computations start, one with the PyTorch model, one with the TensorFlow model, and then the output can be processed by a script to generate a single output, for example, for an ensemble. But of course, you can think about more complicated pipelines. Okay, so this is an example of how to set different types of models. In the case of TensorFlow graphs need the specification of what is the input node and the output node, or the input nodes on output nodes in the graph. So you have to open up the graph using tools like Netron, or by looking into the model, look up the name of the nodes and specify them as input and outputs. The documentation describes how to do that in RedisAI. And then in PyTorch, you don't need to do this, and so model set doesn't need specification of inputs and outputs. Actually, this is the only difference between managing models from different backends. Everything that follows this has a uniform API. So this is quite nice because you can pass this point, pass the model set point where you kind of need to know what the backend is that you're deploying to. Then everything is uniform, and so you can switch one model with the next and your code will not change. Another useful feature is tag. You can tag a model. For example, it's just a simple string attached to the model, but it's useful when you want to know, for example, which version of the model you deployed. So it's up to you to tag the version, but at least RedisAI can inform you about the tag you assigned to a model at a particular key. And if you want to run a model, you typically have to go through this sequence. You set a tensor or tensors. You specify model run with input keys and output keys. Output keys need not to exist necessarily because model run will create them for you. So you then can get the key back in the client, and you see it done for CLI and Python here. While the model is running, you can also get information about that model, not only what is that model or what tag it is, but also what is the duration of the execution since you last reset the AI info data structure, which you can call with the reset stat you see at the bottom. The duration is the duration of the computation in microseconds. And it also tells you how many samples it processed and how many calls it went through. So, for example, we'll see later, you can understand from these numbers how long it's taking per sample. And samples can be batched together, so they can be processed in parallel. And here you will have a number of calls corresponding to the actual calls in a batch, and then the number of samples in each batch. And these numbers accrue in time, so you can really build the statistics and monitoring over what's going on. And the number of errors is also reported. Sometimes we don't want to hit key space, and there are reasons why you might not want to do a tensor set and then a separate model run and then a separate tensor get. Maybe it's just performance, because each time you hit the key in Redis, there's a slight cost for it. And also, if you set up replication or persistent, then that call has to be replicated and persisted. But if you're only setting to run a model and then get the result back, you don't really need to have it in key space wise. It's only of interest to you, to your call. So for this reason, we implemented DAG run, which is a DAG is a direct cyclic graph of commands that you can express as a sequence of commands that create a DAG by if you look at the variables, how the variables are related together. And basically, when you initialize a DAG run, and there's a separator, which is that pipe and greater than sign, everything that follows that has the exact same syntax as RedisAI commands, like tensor set, model run, and tensor get. But in that case, foo is local to the DAG run command. So it will not be seen by other clients. it will only persist in memory without hitting key space, so without being replicated, for the duration of the DAG run command. If the DAG run command fails, that will vanish. And so in this way, we can express a computation where we set the tensor on the fly, run a model where foo and bar are local to the command, and then get the result back as if it is in fact a single command running, so it never hits key space. So really this is a read-only operation in this case. Of course, in the context of a DAG run, you can specify that some of the keys you might want to load them from key space or persist outputs in key space. And we give the possibility of doing that by load and persist. So load will load your tensor from the ref, for example, key in Redis. So you don't need to provide it in context of the DAG. It's just there, and you in the key space, and you get it for the command. And you can also instruct Redis to persist an output tensor. And this doesn't mean that it just persisted. You can also return it with a tensor get. And the output of a DAG run, you see it in the second example from Python. It's really the output of each line that you have in the specification of this little program. So in this case, we have 3 lines, 3 commands: tensor set, model run, tensor get. We'll have 3 outputs, and maybe we're only interested in the last one, bar, which is the output of the tensor set. You can see in Python how we do it. It's kind of a very clean API here, because we initialize the DAG informing the client of and Redis what are the loaded keys and persisted keys, and then we accumulate tensor set and model run with the exact same API as you would do directly on the client. And then when you're ready, you call run, and the DAG will be run at once. And of course, now that we have this construct, we can also build more complicated things like model run or multiple model runs, setting tensors not at the beginning but in the middle if we want, and then run a script. And this is something that we saw when we introduced scripts, the fact that you have a pre-processed script and then 2 models run in parallel, and then an output processing of the results of the 2 network. And we can express those kind of computation here pretty easily. In the future, we'll also do DAG analysis to do optimization of what happens within the DAG. And for example, you can set 2 models into different GPUs and have them run at the same time, and then collect the results in the script. So you can do pretty optimized management of models and script within Redis with DAGs. And a side effect of this is that if you don't specify persist, as we just said a minute ago, DAG run is really a read-only command. With the variant DAG run _RO, we enforce that. We enforce that the command is a read-only command. And so this allows us to run read-only DAGs on replicas, for example. And this is very nice for a master replica configuration, where you replicate your model and then you can hit the replicas to execute your commands. So it allows you some kind of composability of your architecture, and leveraging that to be more efficient. And this is what I just said. You can set a model on the master replicates models and for example, reference tensors, and then using DAG run RO, a client can directly hit a replica or a read-only replica in a cluster to execute what it needs to execute. Like several others deploying in runtime, RedisAI can also do dynamic batching. So it analyzes the queue of requests and takes out the requests in the queue that can be batched up to a maximum batch size and execute them at once, because this is more efficient. For example, if you have a computer vision network that receive many requests for individual images that are not very large in size, it's much more efficient than to take all this in a batch of requests if they're concurrent ones, and then send them all in one shot, and then all the responses are then fan out to the individual clients that requested individual inputs. There's no problem with the temporal sequence of commands here, because you have to remember that model run for the individual client is a blocking operation. So this batching only happens between different clients, and this makes it easy to understand what's happening before and what's happening after in the individual client, as opposed to what's happening concurrently in between clients. If you need to batch in the individual client, you have to do it manually. So you can provide a batch of inputs directly because you know the logic if you are an individual client. And this allows to retain sequentiality in your program, which I think it's quite convenient when you're programming using this. To batch, it's really easy. You can just specify a batch size. Maybe in the future we'll enrich the options for batching, but this is all you need right now to say, if you can batch up to 20 samples for this model, and you specified during model set. I anticipated that we have initiatives to integrate with RedisAI with the lifecycle management tools out there. There's a lot of value in lifecycle management tools, and I think the biggest value is being able to say what happened, who developed what model, and what is the model that is running in production right now. And I think it will be very valuable to integrate RedisAI with several of these. We have done the work for integration, and we are actually in the process of increasing the integration with MLFlow, which is an open source platform for machine learning lifecycle developed by Databricks, and we are adding RedisAI as a target for deployment. So you can deploy directly and experiment directly from within MLFlow, and you can do it from the CLI, for example. You run an experiment, and at the end of the experiment you're satisfied with that experiment or another one, and so if you have the experiment ID that you want to deploy, you just go MLFlow deployments, create target RedisAI, and the model will be the experiment ID, and then you specify the model key at which you want the model to be deployed. There's an ongoing PR. The MLFlow team is doing an amazing work in creating a mechanism by which new deployment targets can be added in the future. So we're very happy about how things are going here, and we'll evaluate other frameworks for integration in the future. This is available as a pip package, MLFlow RedisAI. We, of course, want to know how fast we are, and Redis has the peculiarity of being a very fast solution. We don't want RedisAI to be an exception. So there has been a lot of effort on the Redis Labs side as well as TensorWorks side to make sure that we're not paying for things we shouldn't be paying while we are serving, and how this translates. So the first thing we wanted to see is how RedisAI holds up with a tiny model and a lot of requests. And this is because what we want is serve requests efficiently and minimize the time spent not doing inference. We are not developing a custom deep learning runtime. We're integrating backends, so libraries that can execute individual models developed with various frameworks. So for example, we're running with libtorch in the backend, or at the same time you can have libtensorflow in the backend, or Onyx Runtime, which is a framework from Microsoft for running Onyx models. And we want to make sure that, given the fact that those inference engines will execute with the speed that they have, and the optimizations that were chosen for the network, everything else we want to minimize. So we want to make sure that if you have a tiny model, we are not capped in the number of requests we can serve, just because we designed things in a way that was suboptimal. So we chose this credit card fraud use case from Kaggle, and we built a very small four-layer fully connected network. And we have a version that doesn't use reference data to run, and another version that uses reference data to kind of see how you can run RedisAI efficiently by storing some of the intermediates or some of the state or reference information within Redis directly. Again, we are not comparing raw reference inference speed, because that depends on the individual backends, but we want to measure everything else. So the latency that the AI runtime adds on top of that. To do this, we do everything in the open. You can run things yourself using the AI Bench project that Felipe Oliveira developed in Go. It's a Go tool that already has RedisAI, TF serving, torch serve, and then a REST API around the model that is implemented using Unicorn and Flask. In the future, we'll be extending the benchmarks with larger models and so on, but this was the first objective we had, to scale linearly with the number of clients connected and so on, making sure we're not paying for things we shouldn't be paying. And here you see latency of the various solutions. Lower is better here. In red, you see RedisAI. On the x-axis, there's the number of clients. On the y-axis is the median inference time. So you see that increase in the number of clients, we're very stable in being able to serve models. So more clients don't mean more time to spend doing managing the connections and transferring data and so on. We're very stable at that. And this is a more aggregated view of the same thing. We did our benchmarks on 1 million inferences on a deep learning AMI on AWS on a 12x large VM. And we used many parallel clients to kind of put pressure on the runtime. And here you have throughput. So here higher is better. And also you want to see how it scales, if it plateaus or if it doesn't plateau. And this is what we get from, again, increasing the number of clients, and see how many inferences per second you can achieve. And we can go up to 190,000 inferences per second, increasing the number of requests. And this is the overall inference throughput. Again, the mileage may vary, of course, because this is a very specific use case. We are probing whether the architecture and implementation of RedisAI is capable to sustain a lot of requests and add the minimum amount of overhead over your request, because the premise is you want to use your hardware in the most effective way possible. But of course, in other configuration, for example, when you have large reference data and your runtime is not capable of persisting that reference data close to where the model is running, you may pay even more. Or maybe you don't have reference data at all, and then the model is very large, and so it kind of dominates the amount of requests you can do, just because you're constrained by how long the computation runs. And all these aspects will be studied in the future, and we hope to really optimize the implementation of RedisAI, which is something we want to do, and it's in line with what Redis wants to represent. So what's next? We have big plans for the future. The biggest plan for the future, I think, from my perspective, is taking script to the next level. Right now, with script you can implement pure functions from tensors to tensors using the script API. So basically, you have the whole PyTorch API on tensors in script. So you can run a model. You can run a program and set it in Redis in a text file, but you cannot really call back into models stored in RedisAI. So you cannot call RedisAI commands from within script. Sometimes you want something that can allow you to loop over a model. And looping over a model is something that you want to do in many circumstances. Sometimes is language models. So you want to iterate over a language model, asking one word at a time for the output, for doing what's so-called beam search or other type of search in text generation. Sometimes you want to generate reliability metrics from within RedisAI by running the model multiple times. For example, MC dropout or drop-down connect are ways to perturb your model randomly and generate more than one inference, so that you can then accumulate the outputs and have an idea whether your model of what is the prediction of your model, but also what is the uncertainty around your prediction. And this is a very interesting technique that that you can already implement with RedisAI, but being able to implement just a for loop in script and call model run within that for loop, and then aggregate the result, can allow you to achieve this goal with a minimal amount of data movement as possible. You can do things very effectively. You can also set up aliases, for example, or manage ensembles. Aliases, I assign a key to a model that is not the actual key for the model, but it's one level up. So I can transparently keep two models and do A/B testing without touching my inference program. And being able to call script that calls a model will allow that very easily. And all the way to allowing to backpropagate within the script. So you can, for example, do some sort of fine-tuning or very lightweight learning within RedisAI. RedisAI is not a solution where we foresee that you will do a lot of training, hardcore training but if you have a training script that is very quick, because you are also only fine-tuning one layer of a model, or for example making one step of optimizations. This is something that equipping script to calling to models will kind of enable in the future. So this is something we'll work actively on in the next few weeks. We want to extend the support for backends. Right now we have TensorFlow Lite, PyTorch, and Onyx runtime. A few days ago, the TensorFlow community announced TFRT, the new runtime for TensorFlow models, and we'll look into integrating that as soon as that becomes available and reaches some sort of stability. And we also want to integrate with the ecosystem, more lifecycle management, to make it a very easy target for deployment and monitoring. RedisAI Zoo is something that we want to promote right now. During these weeks, we'll work at setting up a zoo, pretty much like there's a PyTorch hub or TensorFlow hub, Model Zoo, or even Onyx Model Zoo. Sometimes getting from a model all the way to something that can be deployed, and then porting some of the pre-processing, post-processing script so that they are optimally deployable in RedisAI takes a bit of knowing where to look. It's not hard per se, but it takes some time to understand where it goes where. And also, models sometimes are developed in their own way. So you find PyTorch models that are highly modularized, and so it's not obvious how you should export them or trace them to be able to run them on a runtime and so on. So what we want to do is to curate this RedisAI Zoo repo, in which you will find models organized by type, and each type will refer back to one of these models in the TensorFlow hub and PyTorch hub and so on, and have download scripts and eventually export and tracing scripts, and then all the way to setting the model into RedisAI. And this will be very useful to get going. Even if you want to do then fine-tuning on that, it will be very easy to then rerun those scripts and deploy your own models of that type. Or if you have a different model, you can just look in how that is done and do it yourself. For example, the part with I don't know, YOLO with no maximum suppression, how you can not keep it on the client but deploy it as a script. Same thing for beam search for a game phase model and so on. And we'll also propose configuration of scripts and DAGs, and we hope to integrate it as soon as possible with the Python client. So from within the Python client, you will be able to do a number of operations that will allow you to get going in a very few commands. And this will be also integrated with Redis Insight. Redis Insight, as you know, probably is a great UI for managing everything Redis. And in this, we are also planning to have a RedisAI module within Redis Insight, which will allow you to manage models in production and deploy new ones, and eventually download models from the zoo and get running. And also run individual queries to check that everything is running correctly. Okay, I would like to really thank the RedisAI team. We had a lot of fun getting up to this point, and we can't wait for what's next. In the RedisAI, in the Redis Labs team, I would like to especially mention Guy Corland, Itamar Haber, Felipe Oliveira, who did a ton of work on very many aspects from benchmarking to the DAG implementation. Peter Kailo, who had to keep up with our incremental steps taking RedisAI to where it is now. And Rafi Einstein, who is supporting with all the CI building infrastructure, which is quite complex because we have many backends, we have to manage versions and so on. And on the TensorWorks side, I would like to really thank Sharing Thomas, who has been all over the place, and he's maintaining the Python client and creating use cases and helping out with a ton of stuff. So eat us up in the forum. I hope to meet you there. If you have any questions, you can ask them there. If you see problems, you can open an issue on GitHub. I would like to advertise the Redis Beyond Cache Hackathon. At this point, I think it's quite clear that Redis is something that goes way beyond the cache. You can extend the first functionality of Redis. Writing new modules is actually a lot of fun. So you can try to do that, or you can use Redis modules yourself and use Redis gears, for example, to create event-driven programs and solutions. So thank you very much. It's been an honor to speak at RedisConf 2020, and I hope to meet you online as soon as possible and help you out with RedisAI. Thanks a lot.